All right, let's talk about a hidden structure that, believe it or not, organizes pretty much everything in your digital life. I'm talking from the files on your desktop all the way to how a tiny zip file gets made. It's one of the most fundamental ideas in tech, and it's hiding in plain sight.
So let's kick things off with a little puzzle. What in the world could possibly connect the way a tiny zip file is created with, say, the folders you use to organize your photos? I mean, they seem like totally different things, right? But they actually share a secret, really elegant blueprint.
And the answer is the tree. Nope, not the kind you find outside, but a powerful data structure that brings a ton of order to the chaos of digital information. It's really the unsung hero working behind the scenes.
Okay, so here's our game plan. First, we're going to unpack this surprising connection. Then, we'll look at how trees act as your digital filing cabinet and how a computer actually explores them. After that, we'll dive into their secret role in file compression, and finally, we'll wrap up with what makes this simple structure so incredibly powerful.
So what exactly is a tree in computer science? Well, the easiest way to picture it is like a family tree or an organizational chart. It's just a bunch of points connected by lines, but, and this is key, with a few very specific rules that give it a clear top-down structure.
Let's get the lingo down real quick. Every single tree starts at one point at the top. That's the root. Every other point is called a node. Now, if a node has other nodes connected below it, it's a parent. And those nodes below are its children. Simple enough, right? And any node at the very end of a branch, one with no children of its own, we call that a leaf. It's just like a family tree, a clear hierarchy with clear relationships.
Now, where do you actually see this every single day? Your computer's file system. It is a perfect, real-world example of a tree structure that you use all the time, probably without even thinking about it.
I mean, picture it. Your main drive, your C drive or Macintosh HD, that's the root. Every folder inside that drive is a parent node, and any files or other folders you stick inside are its children. It's this simple, intuitive hierarchy. And yep, it's a tree.
So here's the question. If you tell your computer to find every single photo in your Pictures folder, including all its subfolders, how does it do that? How can it be so systematic and guarantee it checks every single spot without getting lost or accidentally skipping something?
Well, to pull this off, the computer does what's called a traversal. It basically just walks the tree in a very methodical way to visit every single node. There are a couple ways to do this, but one of the most common is an algorithm called breadth-first search.
But walking the tree isn't a one-size-fits-all kind of deal. There are different strategies, and the one you choose can lead to some very different results. So let's compare two of the most popular ways to do it.
So breadth-first search is incredibly logical. Think of it like you have a to-do list, which in computer science is called a queue. You start by putting the main folder on your list. You check it for files, and if you find any subfolders, you add them to the back of your to-do list. Then you just move on to the next item on the list. This way you explore the whole tree level by level. It's very orderly, very methodical.
But then you've got a totally different strategy, depth-first search. Instead of patiently finishing one level before moving to the next, DFS is, well, it's kind of impatient. The second it finds a subfolder, it dives straight into it, going as deep as it possibly can down one single branch before it ever bothers to come back up.
Okay, so here's the crucial difference. Breadth-first search goes level by level, which makes it absolutely perfect for finding the shortest path from the start to any other point. Depth-first search, on the other hand, just dives deep right away. BFS uses that organized to-do list, that queue, while DFS just follows a path till it hits a dead end, and then it backtracks. And this is where it gets really interesting. If you were to list out all the files using both of these methods, the lists would come out in a different order. BFS would give you all the top-level files first, but DFS might give you a file from a super deep folder first. The algorithm you choose fundamentally changes the result. Pretty cool, huh?
All right, let's switch gears to our second example, which is just as cool. Trees aren't just for organizing files you can see, they're also the secret weapon behind making those files smaller through compression.
So there's this really clever algorithm called Huffman coding, and it uses a specific type of tree called a binary tree. Now, in a binary tree, each node can have at most two children, one on the left and one on the right. This two-option structure is, as you can probably guess, perfect for representing binary code, which is just zeros and ones.
You see, normally, in a standard system, every single character takes up the exact same amount of space, like 8 bits. It's simple, sure, but it's not very efficient. Huffman coding is way smarter. It gives the letters you use all the time, like E and T, the shortest codes,
and the ones you barely use, like Z or Q, get longer ones.
Just look at the word tilt. The letter T shows up twice, right? So it gets the shortest possible code, just a 1. The letters I and L only show up once, so they get slightly longer 2-bit codes. By using fewer bits for the most common character, the total size of the file shrinks. It's genius!
And decoding it is where the tree structure really shines. You just start at the root of the Huffman tree. You read the compressed data 1 bit at a time. If you see a 0, you go left. If you see a 1, you go right. You just keep doing that until you land on a leaf node, which has your character. Then you pop back to the root and start over for the next one. It's so elegant, and there's no way to get it wrong.
So we've seen 2 totally different uses for trees. What is it about this structure that makes it so flexible and so powerful?
Well, it really comes down to a few basic rules. First, and this is the big one, trees have no cycles. You can't start at a folder, click through a bunch of subfolders, and somehow end up back where you started. That guarantees there's always one and only one path from the root to any other spot. And unlike more complicated networks, a tree always has that one clear starting point, the root.
And that right there is the absolute key. The fact that trees don't have cycles is what keeps algorithms from getting stuck in an infinite loop. When you're searching a file system, you're guaranteed to finish. When you're decoding a Huffman code, you're guaranteed to find a letter. This one property makes the code for these things so much simpler and more reliable.
And the scale we're talking about here is just massive. Get this. The modern Unicode standard, which has everything from English letters to all those emojis on your phone, contains over 149,000 characters. Managing and searching that giant library is only possible because of the efficient, hierarchical organization that trees provide.
So, the next time you're browsing your folders or opening a web page or unzipping a file, just remember that invisible organizer working in the background. Now that you can see the pattern, the roots, the branches, and the leaves, where else are these trees silently organizing your digital world?